Okay, today we start Chapter 5. So in Section 5.1, we're going to talk about quadratic functions. Okay, we already know how to solve quadratics by all sorts of various methods. And now we just want to talk more in depth about the characteristics of parabolas, which come from quadratic functions, and how we can use those to help solve problems. I hope this would be obvious, but let's just write them down anyway. Okay. So let's say we had a parabola that looks like so, something like this. Okay. There's key points on any graph. This point would be the y-intercept. Okay, it would be an ordered pair, some 0, comma, and then a y value. Okay. These would be the x-intercepts, okay, and they're going to come in the form of some x, comma, 0. And these are the x-intercepts. Right. And these could be irrational. Okay, they don't have to be nice even numbers. Another important point on a parabola is either its lowest point or its highest point. That is known as its vertex. And then for any parabola, there is an imaginary line that goes through the middle of this. Because a parabola will exhibit symmetry over this line, that is, if you could lay the parabola over, fold the graph on that line, it would lay on top of itself. And this is known as the axis of symmetry. So let's say this is just some point A, B. Then the equation of the axis of symmetry, because it's a vertical line, is x is equal to this value A. Okay. All right. So let's look at this graph. Okay. So if we had to identify from the graph, the x-intercept does not exist. Okay? And we'll see later that when the graph does not cross the x-axis, what we actually get is imaginary solutions, okay, to solving where the function equals 0. Okay? Now the y-intercept is where we let x equal 0, and so in this case it's the ordered pair 0, 7. Our vertex is here at 3, 1. Okay? And the axis of symmetry is the invisible line that will go through here. Oops, sorry. Okay. And the equation of that line is x equals 3. Okay. So you can just read these things from a graph if you're given it. Okay. Now there's two different ways that we can write equations for the quadratic. Your book calls this the general form, which I think we're used to seeing. That's ax squared plus bx plus c. We could write the function as that. Okay, f of x is equal to that. Okay. We could also, your book calls this the standard form. And I usually just call it the vertex form. That is where you could write the quadratic as f of x is equal to a times x minus h squared plus k. Okay, so I really should have labeled this h and k to stay standard. The vertex usually gets labeled as h comma k. And so why this is the vertex form is when it's written in this form, you can directly read what h is and what k is. So the other way you could find it is that h is equal to negative b over 2a, and k is equal to the function evaluated at negative b over 2a. Okay. So if you have the standard form or the general form, I would just generally go with this. And if you have it in the vertex form, you can just directly read it. Now let's see how we might use this given a graph. Okay, so if we have a graph, let's say it's something like this. Okay. And we're told the vertex is at -2, -3. And this would be the point, this is our y-intercept, 0, -1. Okay. Now this is some translation and variation of our basic parent function f of x is equal to x squared. Okay. But it could be wider, it could be thinner. We don't know. If it was exactly the same, then a would be equal to 1. So let's see if we can write the equation for this. So using the vertex form, y has to be equal to a times some x minus h squared plus k. Okay, well, we know what h is. Okay, so I'm subtracting here from the formula, and from here we see that h is -2. So I'm going to subtract off a -2. That'll get squared, and then I'm going to add the constant k, which is here. So I'm adding a -3. Okay. So we're very close. So this becomes y is equal to a times x now plus 2, that quantity squared, and then -3. Adding a negative is -3. Okay. So if we just knew what a was, we'd be set. Okay, so remember a is either going to stretch it or relax it. All right. Well, to do that, we need some more information. Okay. And we have this additional point here. So we know a value for x and we know a value for y. Okay. So let's substitute those in. And then the only variable we would have is a. Okay. So y is -1 is equal to a times x is 0. Now we can pick any point, but the y-intercept's a good one. Plus 2 squared and then -3. Okay. So -1, we just reduce this now. 0 plus 2 is just 2. 2 squared is 4. -3. Okay. Now let's add 3 to both sides. To get 2 is equal to a times 4. Okay. And then we divide by 4. So we see here that a is actually equal to 1/2. Okay. So this is a relaxing of our basic parabola. And now we can write the function then. So f of x, the equation that represents this graph, instead in the vertex form is a, which is 1/2 times x plus 2 squared -3. So we just did this from the graph by reading where the vertex was and picking the y-intercept. Okay. We don't need the graph. We can determine the equation for any parabola if we're just given the vertex. Okay. So if we're told that h and k, the vertex, occurs at -2, -1, and then we're given any point, just any old point x comma y, to -4, 3. Okay. We can do the same thing. Okay. So we know that y must be equal to a times x minus h squared plus k. Okay. So let's put these things in. This is going to be h, okay, and this one's going to be k. Let's start with that. So y is equal to a times x minus from the formula, and then -2 for h. That'll get squared. and then we add from the formula, and k is negative 1. So not too different from last time. Y is equal to a times x. Now subtracting a negative is plus 2, that quantity squared, and adding a negative is just subtracting. Okay. Good. Now we know what x and y is, so let's put those in. X is negative 4 and y is going to be 3. So we'll have 3 is equal to a times x from above is negative 4, then plus 2, that quantity squared, minus 1. So 3 is equal to a times negative 4 plus 2 is negative 2. Negative 2 squared is positive 4, minus 1. Now if we add 1 to both sides, we get 4 is equal to a times 4. So if we divide through now by 4, in this case we say a is equal to 1. So it goes to infinity just as quickly as our basic x squared. Okay. And we could write that then as a function. So f of x is equal to a, which is 1, times x minus h, which was plus 2, squared, minus 1. Which oftentimes we just leave off the 1 and write x plus 2 squared minus 1. Okay, because 1 times anything is itself. Okay. So that's how you find the equation. Okay. Now, for example, let's say we have some function g of x, which is equal to 13 plus x squared minus 6x. Okay. And I want to write this in the standard form. Okay. Well, this isn't the normal way we see it. We normally see g of x is, we write it in descending order, so x squared minus 6x plus 13. Okay. Now, if we just had to find the vertex to this, remember that the vertex will come in the form, it's an ordered pair where the x is negative b over 2a, and the y is the function evaluated at negative b over 2a. Okay. So in this case, a is equal to 1, b is equal to, because of the subtraction, negative 6, and c is equal to 13. So if we find negative b over 2a, okay, that's a negative, and then b is negative 6, over 2 times a, which is 1. The negative and negative become positive, 6 over 2, which is positive 3. Now, from that, we could take that and evaluate the function at 3. Get 3 squared minus 6 times 3 plus 13, which is equal to 9 minus 18 plus 13, which is 9 minus 5. Negative 18 plus 13 is minus 5, which is 4. So we get the ordered pair 3, 4, and this is the vertex. Now we know that a is 1, so we could rewrite this as f of x is equal to a, which is 1, times x minus h, which is 3, squared, plus k, which is 4. But I'd also like to show you how to complete the square to do this, okay? So let's say, for example, we didn't want to go through all of this. What we could do is we could complete the square, okay? Now, when I'm doing this, it's not like I have an equation anymore. Remember when I completed the square in an equation, I would add something to both sides to maintain the equality. But here I'm going to work just directly on the function. So I'm going to complete something here to make this collapse, but I still have the plus 13. And now to maintain equality, because I'm adding something and there isn't an equation, I need to subtract that off. Okay, but the process is still the same. We'll take b and divide it by 2. That's equal to negative 3. And then negative 3 has to get squared to be equal to 9. So 9 is what I write here, and to help me remember, I write negative 3 squared here. And why I do that then is because this will collapse into the quantity x, and now I can just read from here, minus 3 squared plus, okay, so this is still g of x is equal to, so then we're adding 13 minus 9 is 4. So it's actually a lot less work to just do it this way. Okay, and then from here we can read that the vertex happens at h, comma, k. So now, since this is just a is equal to 1, this is just our basic translation. Okay. Here's y is equal to x squared. Okay. But the vertex is no longer at 0, 0. It is at 3, comma 4. Let me do this in a different color. Okay, so this is just a translation. So this is x minus 3, that quantity squared, plus 4. That's this graph. Or here 3, comma 4. Okay. It is concave up. Okay. Now, both of these graphs are concave up. Okay. And when graphs are concave up, they have a minimum to this function. Okay. So in this case, the minimum value, okay, now the minimum value is the y value. So we have a minimum of 4 at x equals 3. Okay, so you read that from the vertex. Okay. This graph, which our basic one is a minimum, because this is the ordered pair 0, comma 0 for basic y equals x squared, means we have a minimum of 0 at x equals 0. Okay. So these are the y values. Okay. So you can read that from here. So what does that tell us then about the domain? Well, the domain is for both, it's just all real numbers, it's a polynomial. But for this one then, the minimum affects the range. So the very smallest value of y you can take on is 4, and that is included, and then it will go to infinity. With our basic y equals x, we know this, that its range is the minimum, which is 0, and it goes to positive infinity. So if our graph, if our function is given to us in terms of the vertex form, so example, if we have f of x is equal to 2 times x minus 4/7 squared plus 8 over 11, without even graphing this, we can tell you a couple things. A is positive, so this is a concave up graph. Okay. It has a vertex at 4/7, comma 8 over 11. Okay. Because it's concave up, we will have a minimum. That minimum is the y value, and it occurs at x is equal to 4/7. And therefore the range, the lowest value that y can take on is 8/11. It is included and goes to infinity. This is different than, say, for example, if we had this graph. this has a vertex of 3, 4. This is now a concave down graph. Okay. So our vertex is -3, -3, +4. But there's no longer a minimum value because it keeps going down to infinity. Now, instead, there's a maximum value. So this graph has a maximum of 4 at x equals -3. And then that will also change the range. The range now starts at -infinity and goes all the way up to our maximum value of 4, and it is included. Okay, so now let's do a problem where this minimum and maximum qualities of a parabola could help us solve something. Okay. Alright, so we've got a backyard farmer, okay, and they want to enclose a rectangular space for their garden. Okay. Now her backyard is fenced, okay, so there's already a fence here. And this gardener wants to build a garden like so. So this is the fence. The fence already exists. Okay? So to enclose this garden, all she has to worry about are these 3 sides. Now, I don't know what this side is. The side opposite should be that. And then we'll need some length y. And so she has 80 feet to enclose around here. Okay. Oh, I don't know. What does she buy? 80 feet of wire fencing. Okay. So she's going to put wire around here up against the fence that already exists. So what that means is that x plus y plus x, when you put it all together, it can't be more than 80 feet. Okay? She doesn't have more than 80 feet. So in other words, 2x's plus y should be equal to 80 feet. But you know, there's different ways to form a rectangle. I mean, like, should she put the short side and then have it come out? And just how big should this be and how short? These are all sorts of questions. And what she wants to do is maximize the area. Well, okay, we know that the area of a rectangle is x times y. Okay? So this is what we need to maximize. So now I have 2 equations. So this is the perimeter. The perimeter of the fencing, okay, that she has is 80 feet. Right? And here's the area. So how exactly do I determine the x and y? Well, now this is what we call a system of equations. Okay, I have this first equation here, and here's the second equation. In both of these equations, I have 2 unknowns. And I can't solve an equation with 2 unknowns. But if I have 2 equations, I can do a method called substitution. Okay. So if this is true, then I know I could solve this for y, and that y is equal to 80 minus 2x. Now, I can put this in for y. Well, what is y? Y is 80 minus 2x. Okay. So, this is the area. So by substitution, I have really just created an equation in one variable. So we know that the area is 80x minus 2x squared. Another way of looking at this is quadratic. We could write it as negative 2x squared plus 80x. Okay, so the question becomes, is it possible to maximize this area if this represents area? Well, we know here that a is equal to negative 2, and so that means we will get a concave down graph. Okay? And concave down graphs will have maximums. Okay? And that maximum will occur at the vertex. So let's go ahead and solve this and find where the vertex is. So negative b over 2a is negative, and b is 80, over 2 times a, which is negative 2. So this is negative 80 over negative 4, which is just 80 over 4, which is 40 over 2, which is 20. Now, we need to know some things. So the maximum will occur when x is 20. Okay? So let's take our function, the area, and evaluate it at 20. Okay, so that's negative 2 times 20 squared plus 80 times 20, which is negative 2 times 20 and 20 is 400, plus 8 and 8 is 16, followed by 2 zeros, which is negative 800 plus 1600, which is equal to 800. Okay. So the max area is 800, and that'll happen when x equals 20. Okay, so 20 feet or whatever we're working in. Okay, so this is our max area. It'll happen when x is 20. So what if we asked ourselves about the dimensions then? Well, for that we can come back up here. We know that x is equal to 20. So what is that going to make this length of y? Well, I can come right down here. Y is equal to 80 minus 2 times x, but what did we say x should be? Was 20. So y should be 80 minus 40, and y then should be 40 feet. So our dimensions should be 20 by 40. Okay, let's try another one. Okay. So parabolas are very good when you're asked about minimizing or maximizing things. Okay, so here, for example, let's say we're looking for the max product, meaning the multiplication of two numbers. Now, I don't know what they are, but I'm given this criteria. Let's just call them x and y. Okay? The criteria is there's a lot of numbers. When you add them together, they become 6. Okay? So I'm looking at just those pairs of numbers. And now I want to find the pair with the maximum product. Okay, so that is that the product of x times y is what we're looking for. We want this to be maximized. Again, we have two equations. Here's one and here's another. Okay. These are both in x's and y's. I'm not looking to maximize this one, so let's solve it for one. Let's say then that y is equal to 6 minus x. And we can put that in here. So the product that we're looking for will be x times y, but y is 6 minus x. Which we could write this as 6x minus x squared. And if we wanted to write that in the way we're used to seeing it, that'd be negative x squared plus 6x. So again, a in this case equals negative 1. Now that will lead to a concave down parabola that has a maximum. And that will occur at our vertex. Okay? So we need to figure out what that maximum is and what value that is. So here we go. Negative b over 2a is negative 6 over 2 times negative 1, which is negative 6 over negative 2, which is positive 6 over 2, which is 3. Okay? So the max occurs here. Now let's find out what that maximum actually is. So we'll take the product function here and evaluate it at 3. So we'll get negative 3 squared plus 6 times 3. Now here we're only squaring the 3, not the negative, so this becomes negative 9 plus 6 times 3 is 18. So the max product is 9. So what's our other number? Well, okay, if 3 is 1, then we can come back up here. So y is equal to 6 minus 3, so y is equal to 3. So our two numbers are 3 and 3, and they will give a max product of 9. Okay, so let's talk about some more characteristics of this. Alright, so for the intercepts, it's very possible for a parabola to have no x-intercepts. It does have a y-intercept. Okay. It's also possible for the parabola to have only one x-intercept. It's still going to have some y-intercept way up there, but it's possible to only have one x-intercept. And of course, it's very possible to have two x-intercepts. Alright, so this is our y-int. Okay, and way up here is our y-intercept. Okay, here's our y-intercept. Alright. Finding x and y-intercepts is the same for anything, as any other graph. For a y-intercept, you have to let x equal 0. Okay. Now another way of doing that using our function notation is that you're finding f of 0. Now with x-intercepts, you let y equal 0, and using function notation, that means you take the function, because f of x plays the role of y, and you set it equal to 0, and then you solve. Okay, so that's the notation there. Okay, so what should we do here? We should do well, I guess we can do the one we've been doing all along. Okay. So, for example, with our g of x, that was x squared minus 6x plus 13. Okay. So for our y-intercept, okay, that is, we're going to find g of 0, which is 0 squared minus 6 times 0 plus 13, which equals 13. Okay. This is not your y-intercept. Okay. This is the y-coordinate of your y-intercept. The y-intercept is the ordered pair 0, 13. Okay. Make sure you write these as ordered pairs. Okay. Now for the x-intercept, we're going to let g of x equal 0. So that means we have to solve x squared minus 6x plus 13 equals 0. Okay. Let's complete the square now, because we can. Now in this case I have an equation, so I can actually move that 13 to the other side and then just add to maintain equalities. Versus when I don't have the equation, I have to subtract it off. Okay. Well, I think we've done this before, so negative 6 divided by 2 is negative 3. We take negative 3 and square it. to get 9. Now this side's going to collapse into x minus 3 squared is equal to negative 4. Okay. And now we're going to run into a problem here, aren't we? Okay. So as I take the square root of both sides, we get x minus 3 is equal to plus or minus. Now remember, this is the same thing as the square root of negative 1 times the square root of 4. So we have x minus 3 is equal to plus or minus. This is just the number I, and this is the number 2. So x is equal to 3 plus or minus 2i. The problem here is that this is imaginary. Okay? And what that means is that we're in our first scenario here where there are no x-intercepts. Okay? This occurs with imaginary solutions to your function equals 0. Okay? So that's what we did. We took our function here, we set it equal to 0, we came up with an imaginary solution, so there are no x-intercepts. Okay. Now let's do an example, another example with applications. This time we're going to be worried about the height of a ball. So anytime we have a ball, okay, so here's a person, they throw up a ball. What goes up must come down. Okay. And so if you think about extending this downwards, we really would have a parabolic motion, okay, and we have a vertex here. This is a concave down, and so there will be a max height in the air. Okay. Now we just ignore this because it doesn't make any sense to talk about, you know, if this is the ground, the ball's not going below the ground. Okay. Then what we're talking about here is on the y-axis we're talking about the height. Okay. And so this point and this point is where the height is equal to 0. Okay? And there'll be various heights along the way. Okay, so let's see if we can do this. Let's say we have a ball that is thrown upward from the top of a 40-foot building. Okay, so now when I draw my picture, I know that the person is standing on top of the building, okay, and we're throwing a ball upwards. So it starts at this height, and then it's going to go up and come down. Okay, so this is the height. Okay. So we could notice then, we think about this as the point 0, 40. So if we wanted to solve where the height function is equal to 40, well, we know that it's going to happen 2 different times. Here on the way up and once on the way down, and we know that one of those times has to be 0. And we would have to solve for the other. Okay. Now let's answer a few questions before we tackle that question. Right. Now we know that the height function, because it's given to us, alright, we'll need to have this given to us, is negative 16t squared. It is concave down, so it matches our situation, plus 80t plus 40. So what if we were talking about the max height? Well, the maximum height is going to occur here at the vertex. So, okay, let's find the vertex. So negative b over 2a is negative 80 over 2 times negative 16. Okay. Let's do some canceling. This will become positive. 2 goes in there 40 times. 4 goes into 40 10 times. And into 4, 2 goes in 5. So 5 halves. Now this is not the maximum height. So we're moving through, this is time. So this time is 5/2 seconds. So 2.5 seconds. Well, what is the max height? Well, then we have to put that back into the function. Okay. So the height at 5/2 seconds is negative 16 times 5/2 squared plus 80 times 5/2 plus 40. Okay. Make sure you're not using your calculators on these, okay? So you won't have your calculators on your exam. Alright, so this is negative 16. Now 5/2 squared is 25 over 4. Plus, let's just write the rest of this out. Okay. Now let's do some canceling. So we have that 4 goes into negative 16 negative 4 times. So negative 4 times 25 is negative 100. 2 goes into 80 40 times, and 40 times 5 is 200. And then plus 40 times 200, yeah. So that's 100. Okay. So this is 140. This is the max height. Okay, so this is 5.5 seconds. That's when the ball reaches the maximum height of 140. Then we could also ask, well, what time does the ball hit the ground? Okay. So what we're asking here then is, when is the height equal to 0? Okay, so I need to write this up here. So our height is given as negative 16t squared plus 80t plus 40, and I want to know when that height is equal to 0, and then I will find the time. Now, let's do some simplifying here, okay, before we try and attack this. There's a common multiple of 4 in all of these. There may be more. So then that becomes negative 4t squared. 4 goes in there 20 times plus 10 equals 0. And there's still a common factor of 2. So this is negative 2t squared plus 10t plus 5 is equal to 0. And I'm going to hope this thing factors, but I don't want to factor with a negative, so let's multiply everything by a negative 1 to get positive 2t minus 10, or 2t squared minus 10t minus 5 equals 0. Now we only have 2 choices here, so one has to be a 2t and a t. And we have 1 and 5. So I wonder if this is going to factor. Did I do that right? 4. It's in there 20 times 10. 10 plus 5, positive, negative, positive. This isn't going to factor. Okay, that's fine. It's not going to factor. We can still solve it. Alright, so 2t squared minus 10t minus 5 equals 0. Okay, let's do the quadratic equation. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this becomes positive 10 plus or minus the square root. Now here we're squaring the negative and the 10, so this is 100. Let's deal with the signs. A negative and negative become positive. 5 and 2 is 10, and 4 is 40 over 4. So 10 plus or minus the square root of 140 over 4. And we could simplify the radicals and move on as necessary. But for right now, to try and answer the question as an exact answer, here we have 10 plus the square root of 140 over 4. And here we have 10 minus the square root of 140 over 4. Now this is a negative number because if it was 10 minus the square root of 100 over 4, well, the square root of 100 is 10, so we would get 0. Okay? So we're subtracting more than that. So this is a negative time. Okay? Because this x is time. Okay? So this is a negative time, which means it's telling us about this x-intercept here that doesn't make any sense for us. Okay, we don't want to deal with negative time. So the answer, as an exact answer, is this is the time when it hits. And we'll just leave it as an exact answer. Now let's try and answer this last question that we had started. What if we wanted to know at what time the height of the ball was 40? Well, we know the first one's 0. Okay? So let's see if we can find the other one. That is where we need to solve where h of t is equal to 40. Okay? So h of t was negative 16 t squared plus 80t plus 40 equals now 40. Well, we can subtract 40 from both sides to get negative 16t squared plus 80t is equal to 0. And now 8 goes into both of these to simplify this. So negative 2t squared plus 10t equals 0. And we can go even further, can't we? Let's divide by negative 2. So this becomes t squared minus 5t equals 0. And now we can solve this. We can factor out a t. So we have t times t minus 5 equals 0. And then using the zero product property, it's either that t equals 0 or t minus 5 equals 0. So t is equal to 5. We knew this one from the beginning. So the second one, here, at 5 seconds, the ball reaches the ground. Okay, so that's some characteristics for you. We have one last thing to talk about as far as the shape of the graphs are concerned. Okay, we want to start talking about something called end behavior of parabolas. So we have two types of parabolas. We have one, this is concave up, and the other that is concave down. Excuse me. Okay. This one's concave down. Okay, so this one has an a value that's greater than 0, that is positive, and this one has an a value that is greater than, or less than 0, that is, it's negative. And we could put them in the xy plane if you'd like. Okay. Now, if we're talking about the end behavior means we're looking at what happens at x values very large. Okay. So that is, we're talking about positive infinity or very negative. Negative infinity. Okay. Okay, so we look at x values, okay, very large and very negative, and then we say what f of x does. Okay. What do I mean by that? Okay, well, we know that these arrows means that it just keeps going on and on and on to infinity. That is, it's going to keep reaching. So as I'm going to out here to positive infinity, as I look at values of x that are getting very, very large, the function values are also getting very, very large. They are also taking off to infinity. So the way I write that is I say, as x goes to positive infinity, well then the function is also going to infinity. Now let's look and see what happens as x gets very, very negative. So as x is going to negative infinity, what can I say about the function itself? So here's values of x. I'm going to take off to negative infinity. And as I do that, as I'm taking off to negative infinity, the function values still increasing, and they are headed to positive infinity. Let's do the same for the concave down. I want to know what happens as x goes to infinity, as that is, it's getting very, very large. What is our function doing? Okay. So here, I'm going to take off and go towards infinity, and as I go towards infinity in the x, the function is diving. That is, the function is taking off to negative infinity. And we could do it the other way too. Let's look at what happens when x gets very, very negative. Okay? What is happening to the function values here? Well, I start here on the x. Here's our function values. And as x moves towards negative infinity, once again, the function values are diving, and so f of x is also headed to negative infinity. And this is what is known as the end behavior of parabolas. Okay, so that is section 5.1. All right. So it's all about parabolas, their characteristics, and then working with minimizing and maximizing different story problems in real-world scenarios, etc., etc. If you have any questions, send me an email.